So imagine listening to the universe. Not looking, actually listening.
Yeah.
We're talking about hearing these deep, kind of final sounds from black holes crashing together. Scientists sometimes call them cosmic bells.
Right, and recently those bells rang incredibly clearly. So clear, in fact, that they helped confirm one of Stephen Hawking's biggest ideas. And the certainty level, it's really something else.
Yeah, it sounds amazing. So this deep dive is all about what some are calling the clear signal. The official name is GW25111, right?
That's the one. It came from a black hole merger over 1 billion light years away. And what's really key here is that this single event gives us this, well, unprecedented view of what happens right after the merger.
It confirms classical physics, but also, you're saying, opens doors to quantum stuff.
Exactly. It's sort of a bridge.
Okay, let's unpack this then. A signal that clear from that far away? I mean, wow. We're almost 10 years past the first gravitational wave detection in 2015. What exactly was different this time? Why was the signal so much better?
Well, the clarity, or you could say the fidelity, that's the whole story. And it really comes down to technology getting better and better. It wasn't like one single big invention.
Okay. More like steady improvements.
Precisely. Continuous upgrades, mainly to the LIGO detectors. We went from that first detection, which, was groundbreaking, but kind of like hearing a faint, muffled drum,
Right.
to this new one, which is more like hearing all the subtle overtones when you strike a piano key really cleanly.
So the instruments got incredibly sensitive, like surgical tools for space-time itself. You can definitely say that, yeah.
Yeah.
The signal clarity just improved dramatically, and that let scientists really focus on and measure the final crucial part of the event, the ringdown phase.
Mm-hmm.
The ringdown, okay, I remember that term. That's when the new combined black hole is sort of settling down after the collision, shaking off the energy.
Exactly like that. Think of it like a bell. The collision is the big clang when the hammer hits. The ringdown, that's the sound after the clang, the complex vibrations that fade out as the bell stops shaking and gets quiet.
Okay. And because this GW250114 signal was so incredibly clean, so sharp, scientists could confidently measure something they hadn't before. Multiple distinct modes, or specific vibration patterns, in that ringdown sound. Hold on, multiple modes. That sounds significant. What does that actually mean? Like different notes?
Yeah, that's a great way to put it. Think about that bell again. A really well-made bell doesn't just make one pure tone when you hit it. It makes a main note, the fundamental, but also these quieter, higher notes mixed in harmonics, overtones.
Oh, okay. The complexity of the sound.
Exactly. Those extra notes are the multiple modes in the black hole ringdown. There's specific ways the surface of the new black hole is vibrating as it settles. Before, the signals were mostly clear enough just to hear that main fundamental tone.
But this time we heard the harmony, too.
We did, and hearing those harmonics tells us very precisely how the surface, the event horizon, is behaving and settling into its final shape. And crucially, it confirms that shape is behaving just like the theories predict it should.
That's pretty mind-blowing. We're listening to the echoes of something that happened when complex life was just getting started on Earth, and we're decoding its final shivers with, what, incredible accuracy.
Yeah, the precision is remarkable. And like you said, it's not just some interesting detail for a physics paper. That accuracy, that fidelity connects directly to a really big prediction.
Which brings us back to Stephen Hawking.
Right. It brings us right to his area theorem.
Okay, so we measured the ringdown, the final moments, confirming Hawking's theorem. I mean, wasn't that kind of expected? Why is getting to 99.9999% confidence such a big deal now?
That's a fair question. So yes, this signal gives us the strongest proof yet for Hawking's black hole area theorem, but why it matters, especially getting that super high statistical certainty, well, it dramatically reduces the wiggle room for any theories that might try to replace Einstein's general relativity at these extreme cosmic scales.
So it's like the universe itself is signing off on general relativity, saying, yep, this works exactly as advertised, even here. Precisely. The theorem itself, it's a cornerstone of classical gravity, and the rule sounds almost too simple. Black holes only get bigger, they never shrink.
Right.
When two merge, the surface area of the final black hole's event horizon has to be bigger than, or at least equal to, the combined areas of the two original ones. It just can't go down. It's a one-way street.
And the clarity of GW25011 pane, this specific signal, let them measure the before and after areas precisely enough to see that increase really clearly.
That's exactly it. You know, there were previous attempts to check this, like back in 2021, which were really important. They reached about 95% confidence.
It sounds pretty good.
It is good. But in physics, 95% still leaves a bit of space, theoretically, for other things to be going on, maybe subtle effects not covered by the main theory.
Oh, I see. But this new analysis, using those clear ringdown modes from GW25014, pushed the confidence up to 99.999%. That jump from 95% to basically 5 nines is huge. It takes the area theorem from being very likely correct to being this is a fundamental rule within classical physics. It slams the door on almost all known alternative ideas for how black holes merge classically.
Wow. Okay, achieving that level of confidence really changes things. So we know these incredibly violent events follow the rules of general relativity almost perfectly. But if we're confirming a classical prediction, how does this help with the bigger picture? You mentioned quantum stuff earlier. What's the payoff here?
Right. The certainty is really the launch pad for the next set of questions. Confirming Einstein's theory so strongly, especially under these extreme conditions, is a major win. But you asked, why does it matter if GR is classical?
Yeah, because black holes seem like places where quantum mechanics should be important, right?
Yeah.
Inside them, maybe? Definitely. Think of it like this. General relativity is like this incredibly accurate roadmap for the universe's highways, planets, stars, galaxies, even merging black holes. And this result shows that map is, well, practically perfect for those routes.
Okay.
But when we try to use that same map for the really tiny, weird back alleys of the universe, like whatever is deep inside a black hole singularity, or the very first instance after the Big Bang, the map just breaks, it doesn't have the right language.
Because gravity and quantum mechanics don't mesh there.
Exactly. So what we do is use the incredible success of this classical GR map, confirmed so strongly now, as our ultra-reliable baseline. By measuring the ring down so precisely and confirming the area theorem so confidently, we get a very sharp picture of the classical behavior.
And then you look for tiny deviations from that perfection. That's the idea. We use the certainty about the classical part to hunt for the extremely subtle fingerprints that must be there if we're ever going to find a theory that unifies gravity with quantum mechanics. Things like black hole thermodynamics, quantum gravity effects, they might show up as tiny, tiny discrepancies from the pure classical prediction.
So it's like using these giant cosmic collisions happening billions of light years away as enormous particle accelerators or labs to test the absolute bedrock rules of reality.
Yeah.
It sounds like this field, gravitational wave astronomy, is really hitting its stride. What's the pace like now? Are we finding these often?
Oh, the pace is incredible now. You have this global network, the LVK collaboration, that's LIGO in the US, Virgo in Europe, and KGRA in Japan. They're all working together, listening constantly, and they're picking up black hole mergers on average every few days now.
Every few days. Wow.
Yeah, the universe is basically humming with these things. The challenge has shifted more towards refining the detectors, building better ears to hear more details.
And I remember the sources mentioned plans for even better ears, the next generation. What are those instruments?
We're talking about huge projects, really ambitious stuff. There's the Einstein telescope planned for Europe, which would be deep underground, and the Cosmic Explorer project in the US, which would be enormous, built on the surface. These aren't just small upgrades. They're designed to be way, way more sensitive. A generational leap, really.
This generational leap. What's the ultimate goal for detectors that sensitive? What are they hoping to hear?
The ultimate goal is, well, it's kind of breathtaking. They're aiming to be sensitive enough to hear the signals from the very first black holes that ever formed in the universe.
The first ones, like from the first stars collapsing.
Exactly, right back near the cosmic dawn, not long after the Big Bang. Imagine capturing the mergers of those primordial objects. The amount of data and the clarity would be orders of magnitude beyond what we have now. It could let us map out the universe's entire history through these events.
That connects everything. The very beginning of cosmic structure to these endpoints of stellar evolution, probing the quantum origins through these massive gravitational echoes from billions of years ago.
It really is a convergence of the universe's deep past and its ongoing evolution.
So just to wrap this up for you listening, we've gone on quite a journey in this deep dive. We started with this incredibly clear signal, GW25011 fine. Its clarity let scientists finally measure those subtle harmonics, the multiple ring-down modes from a new black hole settling down. And that amazing precision gave us this 99.999% confirmation of Hawking's area theorem, the rule that black holes only grow. But it wasn't just about ticking a box for classical physics.
No, definitely not. It was about using that incredibly solid classical result as a foundation, a starting point, for figuring out the deeper connections to quantum gravity and the fundamental laws.
Right. And as we kind of celebrate how these current upgraded detectors nailed a 50-year-old classical prediction with such stunning accuracy.
Yeah, it makes you wonder.
So what does this all mean? If today's instruments can give us this much certainty about a classical law, What completely unexpected things might the next generation instruments like the Einstein telescope or Cosmic Explorer find? Especially when they start tuning into the quantum whispers from the universe's oldest, earliest black holes, the ones we haven't even heard yet. That's the really big question ringing out now, isn't it?